everybody, and welcome to a video on some examples involving conditional probability. In the last video, we looked at some examples involving conditional probability that used cards, right, or the standard deck of playing cards. In this video, we're going to look at some examples involving coin tosses. An example will be taken from the Skirms textbook on the chapter on the probability calculus. All right, so the problem is going to involve flipping a coin 3 times, right? So we'll introduce language similar to what we introduced on the exam. So H1 is going to mean that the first toss of the coin is heads. H2 will mean that the second toss is heads. And we'll let H3 mean that the third toss is heads. Now, we're given that the coin is a fair coin, so the probability of each toss landing heads is 1/2, and the tosses are independent of one another, right? Learning that the first toss goes heads doesn't tell me anything about whether the second toss is going to go heads or tails. Right? So we're assuming fairness and independence in our probabilities. So the first question that we're asked is, what is the probability that we would get 3 heads? Right? And we can write that in our language here as the probability that we'd get H1 and H2 and H3. Right? Now, we'll work through this one really carefully, maybe more carefully than you have to, but just to see how it all works out. So here, right, this is a conjunction. We want to employ general conjunction rule to figure out the probability of a conjunction, but general conjunction rule applies when you have, right, a conjunct like A and B. So we have to really view this, even though there's 2 conjunctions showing up in here, we're going to view it first of all as a conjunction between H1 on the one hand and H2 and H3 on the other as our second conjunction, right? And then we can apply general conjunction rule. So according to general conjunction rule, this is going to be equal to the probability of H2 and H3 given H1 times the probability of H1. Now, we can apply general conjunction rule again to this next probability here, right? The probability of H2 and H3 conditional on H1, right? Since we know that conditional probability functions are themselves probability functions, as we showed in an earlier video. So we can apply general conjunction rule again. So we get this is the probability of H3 given H2 and H1 times the probability of H2 given H1 times the probability of H1. Now our independence assumptions are going to allow this to simplify, right? Because the tosses are independent of one another, we really know the probability of H3 given H2 and H1 is just the probability of H3. And the probability of H2 given H1 is just the probability of H2 times the probability of H1. All right. So, right, this is a case where because all these statements or events are independent of one another, the probability of their conjunction of all of them is just equal to the multiplication or the product of the probabilities of each of the conjuncts taken individually. So this then becomes 1/2 times 1/2 times 1/2, since we know the probability of it landing heads on any particular toss is 1/2, which equals 1/8. All right, so that's our answer for the probability of all of them landing heads. Next question is, what's the probability that we'd get 2 heads and 1 tails? Right, so probability of 2 heads and 1 tail. So let's think about how we'd write that in our language. So what would it mean for there to be 2 heads and 1 tails? Well, there's really 3 ways that could happen, right? We could get H1 and H2 and not H3, right? It goes tails on the third toss. Or it could be that we get heads and then tails, right? Not H2 and then heads again, H3. Or it could be that the tails comes first, right? We get not H1 and then 2 heads, right? H3, right? So this statement is really equivalent to getting 2 heads and then 1 tails. So this is the statement that we want to find the probability of. But this is a disjunction, right, where each of the disjuncts, right, are mutually exclusive with each other, right? You couldn't get heads the first 2 times and then tails the 3rd time, and also get tails the first time and then heads the second 2 times, right? So this is going to be a case where we could apply additivity because each of the disjuncts are mutually exclusive. So this is really just going to equal the sum of the probabilities of these disjuncts individually, H1 and H2 and not H3, plus probability of H1 and not H2 and H3, plus the probability of not H1 and H2 and H3. Now each one of these, right, is just going to have a probability that's going to be similar to the probability we just computed, right? Because of the independence of each of the tosses, these are each really going to be products, right? The first one's going to be the product of probability of H1 times probability of H2 times probability of not H3 plus probability of H1, probability of not H2 times probability of H3 plus probability of not H1 times probability of H2 times probability of H3. Now, right, we know that the probability of any particular toss going heads or going tails is 1/2, right, no matter what. So these are all going to be 1/2 cubed, right, 1/2 times 1/2 times 1/2, plus another 1/2 cubed, right, plus another 1/2 cubed. Right. Now, 1/2 cubed, right, is just 1/8. So this is really 1/8 plus 1/8 plus 1/8, which is 3/8, right? So we get 3/8 as our final answer for the probability of getting 2 heads and then 1 tail. Right? All right, the next question is what's the probability that we would get 1 head and 2 tails? Probably 1 head and 2 tails. Now here, right, symmetry is going to answer this for us, right? Because it's not more likely that you'd get 2 heads and 1 tail versus 1 head and 2 tails, right? Heads and tails are both equally likely. So in that case, right, this question is just going to have the same answer as the previous one, right? 3/8. So easy given the previous question. Next question, what's the probability of head on toss 1, so H1, and tail on toss 2, so not H2, not H2, and then a head on toss 3, H3. Well, again, right, because of independence, we're going to be able to just multiply these out, just like we did in the part B, right? So we actually already solved for this, right? Probability of H1 times probability of not H2 times probability of H3, which we said was just 1/2 cubed or 1/8. Right? That's our probability there. Next question. What's the probability of getting at least 1 tail? Right? Probability of at least 1 tail. Now, what does it mean for us to get at least 1 tail? That really means that we don't get all heads, right? So getting at least 1 tail is just the negation of getting all heads, right? So this is really the same thing as finding the probability that's not the case that we only get heads, right? H1 and H2 and H3. But then this is finding the probability of a negation, right? Which we can use negation rule to do, right? So we'll do 1 minus the probability of H1 and H2 and H3, right? But we already know the probability of getting all heads is just 1/2 cubed or 1/8. So it's going to be 1 minus 1/8, which is 7/8. So 7/8 is going to be the probability that you'd get at least 1 tail. All right? Not so bad. Next, we're going to do the probability that we would get no heads. Right? Probability of no heads. So that means no heads is really all tails, right? So it's the probability that we'd get not the first one is heads, and not the second one's heads, and the third one's not heads either. Right? But again, by independence, we're able to multiply all these up, right? So it's just going to be the probability of not H1 times probability of not H2 times probability of not H3. So we get, again, each way of these is going to be 1/2 because tails is just as likely as heads. So we're going to get 1/2 cubed, or 1/8. And the next question we want to answer is the probability that we would get either 3 heads or 3 tails. So in our language, we could write that as either all heads, so H1 and H2 and H3, that, or all tails, right? Not H1 and not H2 and not H3. Now, here we have a disjunction, right, in which each of the disjuncts are mutually exclusive, right? You couldn't get all heads and also get all tails, right? The conjunction of those two things would have probability 0. So that means we can add them, right? We can add the probability of H1 and H2 and H3 plus the probability of not H1 and not H2 and not H3. But we already know the probabilities of each of these, right? This one is 1/8, and this one is also 1/8, so we get 1/8 plus 1/8 is equal to 1/4, right? So there's a quarter chance that we would get either all heads or all tails. All right, so hopefully these problems have given you some sense of how we can employ some of these basic probability rules and ideas like independence and conditional probability to answer some simple questions about probabilities of getting different sequences of results when we're flipping coins. We'll get some more practice in future videos and in homework. For this video, just remember to complete the participation poll for it. And then on Friday, we'll look at another result that involves conditional probability that's known as Bayes' theorem. It's probably going to be the most important result from the whole course. So we have that to look forward to, and I'll see you then. Thanks, guys.